So, last time we proved that a Dedekind domain has the property that if you take any non-zero fractional ideal, let us say first any non-zero integral ideal, then it is a product of prime ideals in a unique way up to ordering. Then we can write any non-zero fractional ideal as a ratio of two integral ideals, and hence as a ratio of product of prime ideals, and this way of writing it is also unique. We ended by proving that any ideal in a Dedekind domain is generated by at most two elements. Okay, so it's nicer than just saying that it's Noetherian. Noetherian rings have the property that any ideal is finitely generated, but here we have at most two generators. So, it's much nicer. Today we are going to prove that a ring of integers in a number field is a Dedekind domain. Okay, so that's going to be our aim today. So, let K be a number field, and by OK we denote the ring of integers of K. Okay, and we denote by n the degree of K over Q. This will more or less be fixed throughout the this talk, and we proved earlier. So, we proved that OK is a lattice in a particular vector space that I am not going to recall from earlier. So, it is in a particular vector space which is isomorphic to R to the n, and so OK is a free Z module of rank n. So, this is what we proved earlier before we embarked on study of Dedekind domains in general. All right. So, now we want to prove, our aim is to prove that OK is a Dedekind domain, right. So, what do we need to prove? We need to prove three things. OK is Noetherian, OK is integrally closed, in K. This we did earlier, this was done earlier. So, I do not need to do that, and then I need to show that every non-zero prime ideal in OK is maximal. Okay. So, these are three things, and the second one we have already shown. So, we need to prove that OK is Noetherian. So, let me write that down as a lemma. So, the notation is fixed until we finish the proof that OK is Dedekind domain. So, the lemma simply says that OK is a Noetherian ring. This essentially follows because OK is a finitely generated Z algebra. So, let us so in the proof we will use Hilbert Basis theorem. So, we use Hilbert Basis theorem without proof. I am not going to prove Hilbert Basis theorem for you. What does it say? So, Hilbert Basis theorem, I will simply give you the statement without proving it. If R is a Noetherian ring, then the ring of polynomials in one variable over R, Rx is also a Noetherian ring. Okay. So, this is what it says. All right. So, what does this mean? So, as a consequence, if R is a Noetherian ring, then if you take the ring of finite number of polynomials of finite number of variables is a Noetherian ring. Right. So, that is the first consequence, because I can just apply Hilbert Basis theorem to R x 1, which is Noetherian by Hilbert Basis theorem, and I adjoin another variable x 2, and so I get R x 1 x 2 is Noetherian, etc. Right. So, I can add any finite number of variables. Now, another consequence, if R is Noetherian, then R alpha 1 up to alpha n. So, these alpha i's, these are not necessarily variables now, they lie in some bigger ring containing R, and I am just adjoining them to R. Okay. So, is also Noetherian, because homomorphic image of a Noetherian ring is Noetherian, because there is a surjective map from the polynomial ring in m variables to this ring. Okay. So, xi just goes to alpha I, and this map is surjective, and homomorphic image of a Noetherian ring under ring homomorphism is again Noetherian. So, these are easy things to prove. Okay. So, we get that if R is a Noetherian ring, then any finitely generated R algebra is also Noetherian. So, this is a simple consequence of Hilbert Basis theorem, and this is the one we are going to use. Okay. So, OK is a finitely generated Z module. This I just recalled at the beginning today. Hence, OK is a finitely generated Z algebra. Therefore, OK is Noetherian. That is what we wanted to prove, right. So, the fact that OK is Noetherian is a simple consequence of Hilbert Basis theorem. Okay. All right. So, next we want to show that OK, any non-zero prime ideal in OK is actually a maximal ideal. So, let me say this as a lemma again. Let P be a non-zero prime ideal in OK, then P is a maximal ideal. Now recall, what do we know about prime, what are other characterizations of prime ideals and maximal ideals. So an ideal A in a ring R is a prime ideal if and only if R mod A is an integral domain, and A, an ideal in R, is maximal if and only if R mod A is a field. Okay. So we want to show that OK mod P is a field. Right? This is what we want to show with the hypothesis given in the lemma. We will prove that OK mod P is finite, it is a finite set. Okay. And we know, then use that finite integral domains are actually fields. So this you must have seen in any basic algebra course, that if your integral domain is finite, then it is actually a field. Okay. So there can't be a finite integral domain that is not a field. Alright. So how do we prove that? So I mean we are proving something stronger, right? We are proving finiteness result in order to prove that it is a field. Alright. So more generally, we prove the following. That if A is a non-zero ideal in OK, then OK mod A is finite. Okay. In other words, the index of A in OK is finite. Okay. So more, not just for prime ideals, we prove this for any non-zero ideal. So how do we do this? Well, we proved the following things. So we proved that any non-zero ideal A in OK is also a lattice in V, right. Therefore, A is a free module of rank n, and then we proved a bunch of results about lattices and sublattices. So this shows okay. So that is all there is to it, because A is a OK module, it also gives you a lattice inside V. Okay. All right. So that proves the lemma, and as a corollary we get the following: OK is a Dedekind domain. Okay. All right. So now we have proved that a ring of integers in any number field is a Dedekind domain, and hence we can use all the properties that we proved for general Dedekind domains. Okay. But before going to that, we use something that went into the proof of the last lemma, and make the following definition. So definition, right, we proved that so let A be a non-zero ideal in OK, then we know that A has finite index in OK. So, you define norm of A to be this index. Okay, this is also equal to the number of elements in this quotient ring. And you define, so this defines norm for all non-zero ideals. What about the zero ideal? You just define this to be 0. Okay. So, norm of an ideal right now is a number. Later on we will define norm. So, we will take a relative extension. So, we will take extension L of a number field k, and then we will define norm of an ideal inside L, norm from L to k. So, that will turn out to be an ideal. Right now we are just defining what is called absolute norm, and this is just a number. Okay. So, norm of the zero ideal we just define as the as 0. Okay. So, we want to prove a bunch of things about this this norm. So, the first one that we are going to prove is the following. So, let A be an ideal in OK, let alpha be any element of OK. So, it could be 0. In that case the result is going to be very easy to prove. So, I can take norm of the ideal alpha times A. So, alpha times A is also an ideal. I can take its norm. This is equal to mod of norm from k to q of alpha. So, earlier we defined norm of elements from number field k to q, and that is an element of q. But and when you take an algebraic integer, you get an element of z, but it could be negative. So, we have to take mod of norm of alpha and then norm of A. So, that is what the relation between norm of alpha A and norm of A is. Okay, so, how do we do this? This is just a bit of linear algebra over Z, and some of this we have already done before. Okay. So, I am going to be a bit brief here. So, let beta 1 up to beta n be a Z basis of A, right. We said that A is a lattice of rank n, and so it has a Z basis, and this is our basis. Then what is the Z basis of alpha times A? Then a Z basis of alpha A is alpha beta 1, alpha beta 2, and so on up to alpha beta n. Okay. All right. So, what do we get then? We get the fact that okay. And okay, let me also fix a basis of OK, since everything is defined in terms of OK, be a Z basis of OK. All right. Then when we proved this relationship between discriminant and delta squared, we wrote something like this. Then there exists A an n by n matrix over Z such that why this is such that sigma I of beta j, this is equal to sigma I of alpha j times A. So, these are both n by n matrices. Okay. And recall our notation sigma 1 up to sigma n are embeddings of k in C. So, these are, there will be n distinct embeddings of k in C, and those are denoted by sigma 1 up to sigma n. So, here is a piece of exercise. This is more or less recall from what we had before, that if you take determinant of A, then this is equal to OK, this thing. Okay. So, this is norm of A. So, that is what determinant of A is. Now, the next thing we notice is the following. So, if you take sigma I of alpha times beta j, then you can write this as okay. So, okay, so let me write it like this. So, you can write it as a diagonal matrix. So, I will need a larger bracket here, sigma 1 alpha, so on up to sigma n alpha, and then zeros everywhere else, and sigma I beta j. But remember, this thing is equal to, so I still have my diagonal matrix sigma 1 alpha up to sigma n alpha, sigma I alpha j times A norm of alpha A, which is also index of alpha A in OK. This is mod of determinant of A times this diagonal matrix. But what is the determinant of that diagonal matrix? That is simply norm of alpha. And we already recalled that determinant of the matrix A is norm of A, and so we get what we want, right, k over q of alpha. All right. So, that is a very good relationship to have between these norms. This tells you that now we can extend the definition of norm to fractional ideals. Okay, so let A be a non-zero fractional ideal then there exists x which is in OK, but not 0, such that x times A is an ideal in OK. Right. So, I can define, define norm of A, right. A is a fractional ideal. So, this was not defined earlier unless A is an ideal. So, what I do is I just define this to be mod of norm k over q of x, but now I take its inverse and then I define norm of x a, which is an ideal, right. So, x a is an ideal, so norm of x a is defined now. So, that is my definition of norm of a fractional ideal. Okay. All right. So, our next aim is going to be to prove that norm is actually multiplicative. So, if you take norm of two ideals, norm of product of two ideals, then it's you can first take their norms and then take their product. Okay. So, we are going to prove that norm is multiplicative, but we need some preparation for that. So, today we proved that OK is a Dedekind domain. Our aim is to prove multiplicativity of the norm map that we have defined for ideals inside rings of integers. So, we will continue with the next time.